intersections. The work of this project is basically have been done by me and Kumar, another RA at the lab, and it's been supervised by James. So I guess the name of the project is pretty much self-explanatory. So we're trying to analyze this kind of information that already exists at intersections. But before even getting us started onto like the details of analysis, there are certain things that should be cleared up for this task. The first of which is like is it even worth it to analyze this sort of information, which is basically the movements of the cars at intersections? And to answer that, it is just consider the relevant domains to the traffic analytics. First of which is like the safety of drivers and pedestrians, which is pretty important in terms of legislations and the aims of the government. The second one is the efficiency of transportation. Having this sort of analysis and information in hand via like something like an intelligent traffic signaling, there is room for improving the efficiency of transportation. And thirdly, most of the time, just government or the people in general are really interested in having statistics as a general term for the movements of cars and the traffic itself. The second question that should be cleared up is how available is the data to process? Unfortunately, for the traffic data, there are certain rules in terms of who has permission to gather traffic data, because it is like the roads and intersections are public property, and you cannot easily just gather data. It's not like scrapping the web for some tweets or something like that. The second one is like the privacy terms also apply to gathering the data. So having sort the data, you should be concerned if any privacy is violated, if the plates on the cars are vivid, or if any of the faces are vivid in the data you gathered. With those constraints, still there are a number of public data sets that satisfy those constraints and are in hand, like ASCD challenge data set and the KITI. And thirdly, how accessible this data is. For accessing this kind of data, we have two options. First of which is just install your own camera, or just hire a company that does that for you and gets the required permission that you can gather data. And the second one, and the harder option, is to acquire access to a pre-installed and typically government-owned cameras. I believe that the Transplan, the company we're working with, does the first one. So they install the cameras at intersections for short-term studies of traffic flow at the roads and intersections. All right. So just giving a big picture of the project that we're doing. We're just interested in knowing like who went where, like at the crowded intersection like this, which is in Japan. It would be really interesting to know how the cars move, and even how the pedestrians cross the intersections. There are predetermined movements of interest at each intersections. For instance, in this picture, coming from the left part of the intersections to the right part, each vehicle can take up to 3 movements, marked as movements of interest 1, 2, and 3, which is a right turn and just going through the intersections and taking a left turn. To analyze these kind of movements, we have developed a pipeline which basically consists of 7 major components. The first, just quickly, I will just name the parts and just introduce them, and after that we will one by one individually go through them. So these 7 parts consist of a pre-processing step for removing noise and other different sort of distortions that the video might have. The next step is object detection. It could be 2D or 3D. And having those bounding boxes and the location of the cars and vehicles, we are then interested in reprojecting that location back into the ground plane of the intersection. And once this location is in hand, we are interested in tracking and IDing each individual car so that we can know like which sort of movement it took, from which part of intersection it entered and from which part it exit. And at the end, we have a classification part, which basically groups these tracks and movements into 12 categories. So we have like 3 movements at each entry of the intersection, and each intersection has up to 4 entries. So it would be 12 movements. As for the pre-processing, mostly at each intersection, because of the cost of the cameras installed at the intersections, there are only 1 camera installed. So these cameras should have a really wide field of view, and that means that there would be some sort of nonlinear distortion on it. For instance, on the left picture, you see a straight line for the cables on the air, which is after removing the fisheye distortion, and on the right image you see the unprocessed image, which you see that the lines are curved. And this sort of pre-processing that we're doing is called fisheye distortion, removing the fisheye distortion. And to do that, you need to have the camera intrinsics, and your camera should be calibrated. After pre-processing the data, the very first step that should be done is just localizing the vehicle, knowing its position at the video or the image. The output of this step is basically a 2D or 3D bounding box, just encapsulating the object itself. And for this task, we are using deep learning based models for multiple object detection, or MOD for short. Models, we have tested a couple of models for these parts of the module, including Detectron 2, which was developed in Facebook. It has a ResNet 50 backbone with a feature pyramid network. We have also tested multiple other regularly used object detectors, including YOLO V5 and MM detection from OpenMM Lab. Their performance at this step of our research are almost the same. So we don't think that considering that the goal at the end, which is the classification of the cars, this step is the bottleneck of the pipeline, and these models basically perform the same in our current setting. But at some point, one should decide which model to use, and to choose that model, there are certain things that one should consider. Out of those things, having like the accuracy of the bounding boxes and computation time of the model, because if you wanna have your model real time installed at the intersection, some of these models like they take a lot of computation power and computation time. They could not be used real time, but some of them could, like YOLO V5. And each model has different hardware and software requirements, and that is also a different thing to be considered. To compensate for all these different options and all these different choices we have decided to just wrap this detection module via a condo environment, meaning that in our pipeline, you can easily just plug in and plug out a detector without having to bother yourself knowing what is the software requirement. You should have like a basic software requirement, but you don't have to install it and like configure the software requirements for each model specifically for each intersection. Yeah, and this is a pretty standard results for detecting the cars. We see these blue bounding boxes around the cars, and the cars are just moving through the intersection. And this intersection, which is the baseline for our analysis, is placed at 9th line and Dundas. All right, and after having those bounding boxes, we are also performing some post-processing steps on the data. The first post-processing step we're doing is just filtering out the bounding boxes with lower confidence than 0.75. It means that if a car is, if it is like a bicycle, but the detection model somehow predicts it as a car, but like with less confidence, around something like 50%, our model would filter that out, and we only consider the vehicles that we are sure that it is like a truck or a car. And also because the resolution of the footage we have is high, and the models we use are pretty accurate, cars coming from the far side of the intersections also would be detected really soon, and which is not really necessary for categorizing the cars. For that reason, we have this kind of region of interest at each intersection, which is the bright spots on the image here. And we are just again filtering out the bounding boxes that are not in the region of interest. And yeah, so far we have done all these steps and processes on the camera view. So we are just processing on the image, but we have this idea that reprojecting all these information and all these points and bounding boxes onto the ground, back onto the ground plane, would give us a better view and better power to process and figure out the data we are looking for, figure out what sort of movements the car took. And for that, we are estimating some sort of linear homography, linear transformation from the camera view on the left to the intersection top view on the right. To do that, we have this annotation step in which in which the parts of the intersections that are pretty vivid from both views could be chosen. For instance, in this picture, the lines at the crosswalks are chosen at the points that are vivid in both pictures. And once these spots are marked at the intersection, we have a homography matrix, which is a linear transformation that can reproject the data from the camera view into the top view, and the result would be something like the picture on the right. Once this data has been, like, once we have the homography and we have the bounding boxes, the bottom point of the bounding box would be reprojected onto the intersection, and after that we have this tracking module. Tracking module also similar to the detection module, because it is based on deep learning models. We are wrapping it via a Conda environment, meaning that again, when it is being used and being installed at the intersection in real life, we don't have to worry about the software requirements that is necessary for each tracker. Our trackers are currently following the standard multi-object tracking, or MOT for short, by detection. Meaning that the detection of the cars are performed separately, and after that we have a tracker module. So far we have tested the following models: sort, deep sort, and center track. As for the sort is a real-time tracker in which basically the dynamics of the car is being predicted by a Kalman filter. And and for deep sort, it is basically the same, but at the matching step in which two cars are ID'd and cars in different frames are being associated with each other in terms of being the same car, they are also using a deep features from the bounding boxes, from the image in the bounding boxes. And we have also tested center track. Again, in this part, we have many options to choose from, and the model that I believe should be chosen at last should be dominant in two parameters. First of which is just computation time, because we don't want to waste our resources on the tracking. And secondly is the performance metrics. For multiple object tracking, there are certain metrics that just determine how good your work, your tracker is performing. Out of them, MOTA and HOTA and IDF1 are the most common one. MOTA is multi-object tracking accuracy, and IDF1 is just the FS score of the IDs of each car. In which like IDF1 determines how many re-IDs your model has, meaning that how many times your model just was confused and just replaced the name of the two adjacent cars. Here we have some results from the tracking. In these pictures, the tracker is deep sort, and the detectors and the detection boxes were mined using Detectron 2. So from here we see that cars, the red spots are the beginning of the tracks, and the blue spots are the end of the tracks. And from here we see on the right that cars typically traverse like a determined line or a determined curve at the intersection, and it is due to the rules we have for driving and also for the lines we have on the road, which intuitively like guides people through the intersection. This gives us hints that having those information, having those typical movements and traffic flow at intersection could help us categorize the cars more efficiently. So for that, we have a number of metrics using which we are trying to cluster all those tracks at the intersection. And out of these metrics, CMM, which is short for counter matching map matching, was developed at our lab previously, and we have a paper for that. It is basically a DP algorithm in which the points at two track lists are being matched in a way that it has the minimum cost, and it is used for matching two curves in a 2D space or a 3D space, I guess. And the other matrix we are using is just the cosine similarity or cosine distance between the direction of the cars, meaning that each track has a starting point and an ending point, and you can consider a vector starting from that starting point and ending at that ending point. Having those vectors, we can compute a cosine similarity matrix for between two trajectories. And the rest of the metrics we are using are some sort of a combination, the two of them, because when you are considering the vectors of transition of a track, you are somehow just throwing out all those information about the positions that exist in the track. But CMM, on the other hand, is really sensitive to the position of each point, because it is matching the points at between two tracks. For that reason, we have also developed a number of hybrid methods for SEG. which uses CMM and cosine distances the same way. We also have a metric we developed. For the moment, we are calling it triple cosine, in which instead of modeling your track with only 2 points, which are the starting point and the ending point, you model your track with 3 points, starting the middle point at the end point. So with those 3 points, you have 3 vectors, and we are computing the cosine distance of the corresponding vectors for each track. And once this matrix is in hand, you can compute a similarity matrix between the tracks. It would be a square matrix, and after that, you can perform many sort of clustering algorithms on the tracks. For the time being, we are using a spectral clustering algorithm, which is based on eigenvalue decomposition of that matrix. Meaning that you are finding out the directions in the space of the matrix which have more variation, and you are just reprojecting your tracks into a lower dimension, and on that space you are figuring out which tracks are the same. On this slide, we have the results of our clustering. I believe the top row, the T cosine, is performing pretty well in terms of clustering. These pictures all have 12 clusters because we are interested in 12 movement of interest, and each color represents each different color represents a different movement. For T cosine, we see that the right turns, the going throughs are basically the same color, which is a good thing, meaning that our distance and our model is basically representing a simple and fast model of the tracks, and the distances are also consistent with reality. Once these tracks are clustered, we are feeding the data into an annotation part. The annotation part is not as exhaustive as annotating a video for tracking or detection. It is just labeling 1 or 2 tracks for each movement of interest. And for this step, we present the tracks in clusters to the user, and user just goes through the clusters and chooses the movements, the track that he thinks is a good representative of the movement of interest. And yeah, and after we have these annotated tracks, which are a few, in my own opinion, it could be a lot, but like having 3 annotated tracks for each movement of interest is enough, which is exactly the number that I chose for the classification part. And once we have those tracks, we can actually perform the classification. And for classification, again, we can choose any of these similarity matrix, because like this is the same, because the tracks were coming from the clusters, and we saw that the clustering is performing good because consistent